All right. Hello, everybody. Thank you very much for having me this morning, and thank you for inviting me to present this introduction, this keynote today on quantum technologies. So, I'm Karl Thibault, as was mentioned. I work at the Institut Quantique in Sherbrooke, and today I'll try to give you a quick sense of what is quantum. So maybe just to give me a quick idea, who in here would say that they know what quantum properties are and they could explain them quickly, Show of hands. Okay, so half of the room, a little bit less maybe. Okay, so that's good. That's good. All right. Um, yes. So this is the plan for today. So first, I think this first bit on quantum will be useful to a lot of you. I'll leave it very high level, but I hope it can give you a sense of what quantum can do. Then I'll talk a bit about cybersecurity because I think in the context that we are today and for this workshop, it's very useful to have a better idea exactly of what quantum can do for cybersecurity. Then I'll come back to the international context and give my own broader view here of what this all means today. All right, so quantum. So what is quantum science? Quantum science is, at its core, the theory that describes the behavior of matter and light. So it's very broad. It describes basically how our world functions. And it's often viewed as the science of the infinitely small because that's where the weird quantum properties happen. And we'll come back a bit to what these properties of quantum are. Quantum technology, on the other hand, is basically just a new generation of technologies, either electronic or optical, oftentimes, that use these weird quantum properties to significantly improve performance compared to other existing technologies. If they don't significantly improve performance, then they're not really relevant. Like the fact that they're quantum doesn't make them useful. They need to actually be useful compared to what we have today. So let me give you a couple examples. Quantum is actually everywhere already today. GPS is actually a technology that uses quantum technology. They're part of what we often call the quantum 1.0 revolution that happened since they discovered quantum 100 years ago. These technologies, as GPS, use quantum properties, but we don't necessarily control quantum properties themselves. We just know how the world functions, and it enables us to create these technologies. Another one would be MRI. So when you take an MRI scan at the hospital, there are superconducting magnets in here that allow us to create a huge magnetic field to image your body. And these magnets that are superconducting, we know how they function because of quantum physics. Lasers, so the pointer I'm using right now, we couldn't create if we didn't understand the nature of the world, if we didn't understand quantum properties. So now moving on to electronics, all your phones, your computers, these transistors are at scales that are so small that we need to understand quantum properties to actually be able to create our classical computers of today. So classical computers are transistors, and all these transistors are basically switches that could be on or off. And so when a switch is off, we say it's a 0, and when a switch is on, we say it's a 1. And all of this are bits, and this is what we call classical computing. So in classical computing, we have switches that are either on or off, that are 0 or 1. However, in quantum, we have quantum bits, qubits, and these new transistors, these quantum transistors, can be at the same time 0 and 1. Okay? So I'll go a bit deeper into this because I think it's useful for people to have a quick sense of what quantum computing means and what qubits are. So the analogy that I like to use is this spinning money? Spinning coin. Yeah, spinning coin. So what I just told you about 0 and 1 is the quantum property that we call superposition. So let's say you have a piece of a coin and you make it spin on a table. While it spins, it is kind of at the same time 0 and 1. And before you measure it, before you touch it and it falls, you don't really know at what state it will come out, right? But when you do, it collapses, and then you can measure either heads or either tails. So this is a bit like quantum computing. The difference is this coin, you cannot control it while it spins and do computations on it. But with a qubit, while it is in a superposition of 0 and 1, you can actually control it. You can send signals on it. You can manipulate it. And this fact is what we typically, where we differentiate with quantum 1.0 technologies, where we used quantum states, but we did not control them very in a detailed manner. But now in new quantum technologies, we are able to create these states of superposition, and we can control them very discretely over time, and we can compute with them. So this is what basically the analogy I like for the qubit. So what this means is that if you have 300 quantum bits, you can actually represent, using this superposition, 2 to the 300 states. Compared to with classical bits, if you have 300 transistors, you cannot do this. This 2 to the 300 is a huge number. It's actually a bigger number than the number of atoms we have in our planet, and it's actually a bigger number than the number of atoms that are in the universe. So even if we wanted to create a classical computer that could compute this number, we could not, because there would not physically be enough atoms for us to actually create the transistors to compute this number of states. With a quantum computer of about 300 qubits, you can theoretically compute states that are this big. So it just gives you a scale of what quantum computing can possibly do that classical computing cannot. Physicists typically don't necessarily like this analogy because it's not exactly true, but it's still, it gives you a sense of what these qubits can do. Now, another important quantum property that is interesting is entanglement. So before with superposition, I just had a single quantum state. Now let's say I have 2 quantum states. I have 2 quantum coins. And I make them both spin, and somehow I make them interact together while they're spinning at first, while I create these states. Then I can create entanglement. What that means is if I had my own spinning coin, I let it spin, I don't touch it, I don't measure it, and I take the second one, which is also still spinning, and I give it to you, and you take it home. And then an hour later, I decide, okay, I'm going to measure my quantum coin. And I touch it, I measure it, it falls on heads. Then I will know for certain what state your quantum coin will be in when you touch it and you measure it. And this is another very weird quantum property that we don't have any logical, rational comparison in our daily lives. But this means that you can kind of control in some way the total state with just part of it on your end. And this is very, very useful in quantum communication, for example, in establishing cryptographic codes for quantum communication. So entanglement is when you have multiple states, and superposition is when you have only one state. So are there any questions? I think I should take questions now if there are on these topics. No? Okay, clear? Okay, good. All right, so sorry I did not translate this slide because it was way too long, but I'll try to just go over it quickly. So this is a picture that we created at Institut Quantique a couple of years ago. I think it's nice to explain the different steps. So in the middle here, there's quantum principles, so entanglement here, superposition, and interference, which I didn't talk about, but we can go into it if you're interested. All these quantum properties are at the basis of different quantum technologies. Quantum technologies are typically devised into 3 categories. So the first one is quantum sensing, the second one is quantum communication, and the third one is quantum computing or quantum information. All of these have different applications, and all of these are basically completely different. They're all quantum, but you should see them as 3 completely different kind of technologies. So quantum sensing, for example, has applications everywhere there are sensors currently, which is basically everywhere in our society, which has been even increasingly grown in the past decades. So basically in medical and security, in geolocalization, telecommunication, automobile, and construction more and more. Quantum communication, on the other hand, is focused mostly on cryptography, trying to get signals from one place to another, and oftentimes they are linked with quantum information, but you should see them still as different. So quantum computing is the use of quantum states to compute certain problems, just like your computer would. But then sometimes you would need to send that information while it is still quantum to another place. And then this is when you use quantum communication. But often when you do quantum computing, at the end you get a classical signal that you measured. And this you can just send over classical communication channels that we have already in place today. So depending on what you need to compute, then sometimes you need to use quantum communication between steps, but often you don't. Was that clear? Yes? Okay. All right, and quantum computing, which is what I think most people hear about these days, has a lot of applications, namely in finance, pharmaceuticals, and quantum chemistry, transport energy for optimization, and can have some links with artificial intelligence, but this is still a very active field of research. Quantum machine learning, for example, is still very much at the deep tech stage. Okay, so a couple words on who we are in Institut Quantique and who am I to tell you all of this. So Institut Quantique is in Sherbrooke. It was created 10 years ago. We just celebrated our 10-year anniversary last week in Sherbrooke. So it is 45 professors of 4 faculties. It's over 250 students, about 35 people in the technical and professional team, and over, I think now, 600 people that graduated since 2015. So we're a big research institute. We are an interdisciplinary research institute. The way institutes work at Sherbrooke is they are kind of outside the departments, and they try to bridge between faculties and between departments. So we have professors of physics, of course. Basically, the whole department of physics is our members. But then we have members in engineering, in management, in information science, mathematics, chemistry, of course, and also in the School of Applied Politics at the Faculty of Arts and Humanities, which a project I'm working on, which I'll give a few words at the end of the presentation. So in terms of science, what we do can be categorized in 3 places. So first of all is quantum materials. So quantum materials is trying to understand the matter of which creates our daily lives, and to try to find unconventional properties that are due to quantum mechanics. For example, as I said, superconductors are one type. Superconductors, we still don't understand all classes of superconductivity. In basic superconductors, we understand very well, but for example, it would be really great to have superconductors that work at room temperature. In Quebec, when we create hydroelectricity up north and we take it down to Montreal, I think we lose about 30% of the electricity. If cables in these high voltage lines were created of superconductive material, then we would lose 0%, for example. So they're material that have no resistivity. So that would be a good application of this. Quantum information, I just talked about, but basically it's the exploration of quantum phenomena for information processing purposes. We work on many types of different qubits, spin qubits, superconducting qubits. We work also on error correcting codes and on quantum algorithms. And we also work on quantum engineering. So engineering can be used in 2 ways for quantum. It can be used to create new devices, and it can also be used to create technology that enables quantum, for example, quantum computing. Quantum computing takes a lot of very state-of-the-art experimental material like in the lab to create. So we need quantum engineers to help us with these experiments. And we also can create quantum sensing, quantum sensors, quantum photonics, cryogenic electronics, and single photon detectors, mostly for quantum communication. So we're not alone in Sherbrooke working on this. So I'll come back a bit to this later, but I think it's important to also mention that in Quebec, our government has this idea that every city should have a theme. And Sherbrooke was one of the first two to be announced in 2022 and was named the Quantum Innovation Zone of Quebec. So the whole city now has this a non-for-profit, which is called District, which manages the ecosystem. And we are just but one part in here of this whole ecosystem. So in it, we have what we call the integrated innovation chain, which is us and other institutes in the Faculty of Engineering, and a big clean room that enables you to create your technologies, to fabricate them. Then there's a lot of established quantum companies that came to Sherbrooke to work with us. Some startups that were created in-house, but that also came. So Nord Quantique, we don't see all of them, but there's SB Quantum, Cubic, and I think there's Chemia that I added that are from Institut Quantique, ex-students now working their own startups. And there's the whole support ecosystem here with international outreach, financing and coaching and infrastructure to help these companies and these startups to actually create their new technology. So our role at Institut Quantique is to feed talent to this ecosystem. So we have dedicated programs at all levels, including the first undergraduate in quantum information science. We have a quantum computing platform, which is called the AlgoLab, which gives access to IBM Quantum and also to other hardware in the near future to help with collaborative projects to try to create quantum algorithms, but also use them on real hardware to solve concrete problems for our partners. Very, very similar to what was said yesterday about the Maison du Quantique's PAC program. And we have, again, the integrated innovation chain, including our Quantum Fab Lab, which is our experimental platform, the 3IT and the C2MI with the clean rooms to fabricate new devices. So in terms of quantum expertise, we have different initiatives that can help train anybody, basically. So we have Curieux Quantique, which is a popularization program that can start from high school or college students to get them in the pipeline. As I said, at Institut Quantique, we have undergraduate and graduate programs to train students. And then in the short term, we can also train professionals, either in experimental physics or in quantum computing with the AlgoLab. And we also do training at the industry and government levels with daily workshops, for example, or over the course of multiple days workshops, depending on the needs of our partners. And if you can take one message from the past like 3 or 4 slides that I told you, is that beyond technology, quantum advantage is also talent, meaning that you need to have people that can actually work this technology. Otherwise, the technology itself isn't very useful. And there is a talent shortage right now still in the whole ecosystem. So our role, I think, is very key in this. All right, moving on. Oh yeah, one last slide. If you want to come visit us, this is our new building. So feel free to tell me if you're coming to Sherbrooke. It'd be a pleasure to host you. All right. So cybersecurity. I'm going to say a few words on this very important subject. So quantum computing and cybersecurity. Oftentimes people talk about the quantum threat. So what it is, the quantum threat is that public cryptographic codes today that we use in our daily lives when you connect to your bank on the internet, these codes are based on mathematical problems that are hard for classical computers to solve. And hard here means that we can solve them, but it would take like 10 years, okay, using a supercomputer running for 10 years straight. However, these problems are not necessarily hard for quantum computers. Especially, so these are different cryptographic algorithms that could be used classically. RSA is the one that we typically use on the internet, and RSA would be completely no longer secure if we had a quantum computer. Why? Because RSA is based on the difficulty of finding the prime factors of a large number, which is a classically hard problem. But it's an example of a problem that a quantum computer could easily solve if we had a good enough hardware by using an algorithm, which is Shor's algorithm, that was found in 1997, and that kind of relaunched the field of quantum computing at the time. So the question that we should ask ourselves now is, well, when is this going to happen, right? Like, when is a quantum computer going to be strong enough to break these codes? So every couple of years, the Global Risk Institute and Michele Mosca from Ottawa create this, from what? Waterloo, sorry. Yes, sorry, Waterloo. Create this quantum threat timeline report where they ask experts in the field when they think that quantum computers will be able to crack RSA. So basically, here is 5 years, 10 years, 15 years, 20 years, and 30 years, and the likelihood of the estimation by different experts of is by, in 30 years, are we going to have quantum computers strong enough? The likelihood, 99%, 6 people thought that yes. Now, if you look and you take a look at this, it's very hard to interpret, clearly, but I would say that in 15 years, there's more than half of the people that think it'll be more than half likely that it happens. So this should be an indication that, maybe it's a very real possibility that in 15 years, we're going to have quantum computers strong enough. So let's think about maybe, being secure by 15 years, right? And then further from this, you need to think about, okay, how long will it take to migrate current technology to new technology that will be secure? And further, you also need to think, well, how long in the past should my communications also have been secure so that they aren't cracked? Because today, your communications or the US government's communications are not cracked, but they are intercepted and they are stored in big data centers where at some point, maybe they'll be able to crack them. And so if you want your communications that you send today to not be cracked even in 20 years, because in 20 years they might still be relevant today, then you need to have them secure way before they actually have access to a quantum computer. So this is what they say they call the threat timeline. So your threat timeline should be shorter than adding the migration and the shelf time. And 15 years is maybe when quantum computing will be strong enough, and 15 years is way too short for example, for national security level communications. In 15 years, if they crack the communications of today, it could have an impact. So it's very important to try to think about this today. Quantum also offers the solution to these problems. There's post-quantum cryptography, which is algorithms, classical algorithms, that can resist known quantum attacks. I specify known because maybe new quantum attacks will break even post-quantum cryptography. There was a challenge by NIST a couple of years ago to find best post-quantum cryptography codes, and they just began launching them in the field, I think last year. So this is already done in some sense, up to a certain extent. And there's also purely quantum cryptography, which uses quantum properties to establish directly its cryptographic protocol, and quantum key distribution is the most common form. However, QKD is very resource intensive, and it's not very likely that it'll be implemented at large for all communications. It would take just way too much energy and strength to actually achieve. So probably for people, for the large communications, we'll use post-quantum cryptography, and in certain very specific cases, QKD will be used when we need more secure communication. How does this all fit in the international context of today? So today, the quantum effort worldwide looks a bit like this. So all of the countries that are listed here have national strategies, and are the numbers of money that is going into the strategy is listed underneath. So Quantum is very much worldwide, but as you can see, there is pretty much a line in the middle here where there's quantum up and there's no quantum down. So that's also something to keep in mind. The global south is very much underrepresented in this. In terms of investments, there's been a lot of investments in the past decade in quantum, but you can see that most of it has gone to mostly United States. Canada is actually second. So in terms of capita, Canada is one of the most well-funded countries in quantum, although this might change in the near future. And total capital raised by country is listed here. So United States, very much high, United Kingdom, Canada, and France is not too far in fifth. However, over the years, in the 2000s, there were not much funding, or not much funding rounds of startups. And then it really ramped up at the beginning of 2020. And now we see a little dip. You shouldn't look too closely at 2025, but there is still a little bit less funding in 2024. And in terms of capital itself, we've seen a dip, but in 2024 there was actually a big small raise. So I mean, quantum is still going very strong, and we don't see a quantum winter coming up like now. Maybe at some point in the future, but to me it's not very likely. In terms of patents, over the years, at first there were more patents in quantum communication in yellow than in other categories, quantum computing, quantum sensing. However, recently there's been a bit more in quantum computing over the other two. So if we look at the total since 2014, there's still a little bit more in quantum communication, but it'll probably be, quantum computing will probably catch up very soon. Who creates these patents? Mostly China. Also the US, mostly in quantum computing, but in quantum communication, cybersecurity, all of these issues, it's mostly China. If you look at main assignees in terms of different companies, but you can also see with the legend where they come from. In quantum computing this time, not quantum communication, only computing. You see that IBM, Microsoft are the big ones, but then you see a couple companies from China also being in there. So Baidu, I don't know most of these Chinese companies, but you can see their names. So all of these patents, I think it's interesting to see where they come from and who creates them from a regulation perspective. So just gives you a quick idea of what the landscape looks like. So a couple of highlights to me of what this all means. Quantum computing development is seen kind of as the space race of this 21st century. It's the big new tech and everybody's racing to get it. It's dual use, especially in the context of cybersecurity, and it's led to kind of a new Cold War in terms of technology between the US and China. Many countries used their COVID-19 rebound plans to kickstart their national quantum strategy, which was interesting to me. And since we're in France, and I'm Canadian, wanted to mention that Canada and France are very well known in the field for their strength in quantum. But we should not sit on it, and we should actually invest more, because many countries are rapidly closing the gap between us and them. And if we want to remain relevant in these races, we need to stay focused. All right, and now I'm going to take a step back and try to give you my overview of what this all means. If you know a better term for this, then I'm all ears. I don't really like saying broader view, but so yeah. All right, so the question I want to ask now is, what can we do to maximize positive impacts of these technologies? Which I think is, today, the question that we should ask ourselves. So, what does this mean? Well, let's go through a couple of potential impacts. I'm not going to tell you everything, every possible impact. I definitely alone cannot think of all of them, but here are a couple ideas. So in terms of privacy, cryptography and cybersecurity, we can ask ourselves the question, is our data protected? Quantum computers that will be able to crack these cryptographic protocols before the migration time to these new technologies are a threat today. National security is especially problematic, and it's unclear to me yet if individuals like us will be able to be protected as well as governments or big industry. So this is a question that we should ask. In terms of accessibility, we need to ask, do people actually understand what quantum technologies do? If you don't understand what these technologies do, then you can't use them. And then if you also need to have access to them to be able to use them, and you also need to be able to access them, but to have priority of use, because even if they're open access, for example, but when you launch computation, you're in the queue and you're always the last one in the queue to compute, then you don't really have complete access to this technology. So these are 3 questions that we can ask. And then we can ask, to what end are we going to use these technologies? So they are dual use. We need to figure out what are the military uses of quantum technology, and we need to ask, should we or how do we regulate these? And a question that I personally like a lot is, how can we ensure that this new computing power is dedicated to the common good and not for the good of specific wills? And to answer both these questions, or all 3 of these questions, I think societal dialogues are essential, and we need to discuss these with a broad community, not only quantum scientists like me, but with people like you and with broader civil society, to define what is positive and what measures can we put in place to ensure that we put our efforts in the positive. And it's also important to think about what potential negative impacts these technologies can create, so that we can try to negate most of them. And as AI taught us, we don't always think of them in advance, but we can at least try. And so I think this is especially important in the context that quantum is not anymore something that scientists do by their own in their lab. Especially locally for us, it's now a citywide project. Everybody in the city has heard that there's this new innovation zone. Most citizens now know that there's a quantum innovation zone, but they have no idea what it means for them. And so it's important to talk with people and to make them understand what quantum is, and to have these discussions and ask these questions that I posed before with all of these, but also with the city itself. So what can we do? I think the key word, and it was mentioned yesterday also by Professor Vermas, is to anticipate, or try at least to anticipate what will be the impacts of quantum technologies, what problems they'll solve, in what economic or social sector would be useful, how will these solutions impact people, but not only scientists, but everybody, and how will they transform our society or way of life. And our answer to these, or our attempt to answer these questions, is the Quantum Dialogues Research Project. I'll say a few words on it. So the Quantum Dialogues is 3 dialogues. We divided it in 3. The first one is a local dialogue that we have with people in the city that are involved in quantum, but also with civil society. So the Chamber of Commerce, for example, is involved, the Regional Council on Environment, the museum, so people that will be impacted at some point by these technologies. Then we have a national dialogue with people all around Canada that are participating. And we have also a dialogue directly with researchers in quantum and entrepreneurs in quantum, where we take the issues that were raised in the other 2 and we feed them back to the researchers and try to get their feedback on how they see their role in what was brought up in these meetings. The way we do these meetings is something completely new to me. It's very refreshing doing social sciences. I'm used to being in the lab and gathering data and analyzing it, with code. And then here I'm just sitting in a room listening to people talk, and that's the data basically. And then we analyze what people said, and we try to make use of this. And it's very refreshing. I think it's a great way to do science. And I just want to mention that I really appreciate it. So in conclusion, quantum is still very much a nascent technological field. I told you about many uses, but none of them have been really realized today. Quantum computers are still very much At the research stage, we can use them for toy problems, but we cannot do anything useful with them today. If anybody tells you otherwise, they're lying, honestly, to you. A lot of research needs to be done to create useful quantum tools. I would say maybe one caveat. Quantum sensing is some of the sensors are very much useful today. So applications of computing especially are not clear because quantum hardware is still in development. And in my opinion, not enough work is being done to create useful algorithms for what it will actually be used for. But nevertheless, even if this is still true, actually it makes it even more important, I think, to ask the questions that I posed before now, because we can still steer the field in the right way. And I think Professor Vermas said yesterday that in part, social sciences' role is to actually help do that. And I very much agree with this sentiment. And we can also help decision makers anticipate large impacts that will come in the future and try to be ready when a disruption happens suddenly, just like ChatGPT arrived and we weren't ready to regulate it, and we still haven't regulated all of these models. But if we anticipate enough, then maybe for quantum the hope is that we could regulate in advance. And to me, all that I said can be summarized in 2 words, which are responsible quantum. And so I invite you to look more in this field and to contribute to this with me if you're interested. And with this, I'd say thank you.
We know that it's not because we can technically do it that we have to morally make it. So especially in social science, we put interest in balance, what it can bring to society and what it can take off society. You say that in your presentation, what we can do to maximize the positive effects. And for AI, we know that we have a lot of positive things of many era, environments, healthcare, etc. But in the same time, we generate a big quantity of useless picture just to follow a trend on social media. So I come from my question. If I understand well, quantum technologies are developed in industrial dimension for a very specific use case. So we're not going to have quantum computer on her desk tomorrow. But I would like to know if the state of art preview a general and daily use of quantum technologies and what form it will take. For AI, we have the ChatGPT moment. So what about quantum technologies? Thank you.
Yeah, thank you. That's a great question. So maybe one word on the first part, the comment. So to me, the question is not whether we should do it or not, because I think somebody will do it. The question is, how should we regulate it, or how can we develop it in the right way, steer it the right way? And for example, for AI, if we had anticipated that these large language models would be accessible to everybody and that everybody could use a lot of energy to generate useless cat pictures and instead of watching useless cat videos, but if we had anticipated this, we could maybe have regulated it and say, well, everybody cannot use it for more than X pictures because at some point then we generate too much energy, use too much energy, and we don't want this. If we had thought of it in advance, we could maybe have regulated. So for quantum, it's still very unclear. I think the biggest sectors where people anticipate they will have impact, I'd say in the next 5 to 10 years, is quantum chemistry. So, and for simulation of nature. So nature is quantum mechanical. Using transistors to model nature is very hard. So using our classical computers to calculate, for example, the configuration of molecules is something that is very complicated. We have many hard techniques to do that use a lot of energy or a lot of classical computing power. Quantum itself is quantum. Quantum computing uses quantum properties so it can model nature better or with less resources. Depending on architectures, it's even, we're literally simulating the molecules with the quantum bits. So this has applications everywhere, for example, in pharmaceuticals for new drug discovery, but it can also be used for helping us have more efficient processes. So one thing that we use 7% of the world energy today is to create new fertilizers. And we use this process, which is called the Haber-Bosch process, but we know that it's not efficient, but we don't understand how to make it better. Quantum computing at some point might be able to help for that. It could also be used for catalysis for different other reactions to help them become more efficient. So the question is, there's many problems where it could be applied, and if we don't steer it, then it'll go towards the places that have the most money already, for example, financial institutions or pharmaceuticals. But we could steer it in some ways, at least, to help it be more for the common good. So that's why you need to think about it beforehand. Did I answer the question? Thank you.
Okay. I have a question about. No, it's a request. Can you make more clear why it's a bad race? Because the notion itself of having a race, it seems okay. If you would change in your presentation quantum with the energy transition, you could also have all these charts about how China is investing, Europe is investing, and then all of a sudden it's a good race. Why is this? Why should we worry about this race? What's your view about it?
Yeah, I don't necessarily see it as a bad race itself. I think the biggest issue with the race is access. So if one country creates a quantum computer first, then it'll have a big advantage that it can crack codes, for example, cryptographic codes of other countries, while the others don't have access to this tool. So I think this is one way that, one issue that should be raised, meaning, once a quantum computer happens, it's going to be such a disruption that it should not be closed to access to just one specific entity, because it's such a big disruptor. So I think that's the main issue I see with the race itself. But I mean, others are probably going to be close. It's just like, it's kind of like the bomb, right? Like the nuclear bomb. If one person has it and nobody else has it, then it's... Yes, yes. Yes, an arms race, yes, thank you. Yeah.
Hello, Ludovic Perret, I'm professor of computer science at EPITA, and thank you for your nice talk with all these charts. It was very interesting. And so, first is one remark about investment. So in Europe, we are discussing a lot about a new Quantum Act, which will occur by the end of the year. And the trend is that the investment will be quite significant. So we are speaking about 5 billion. So it's not official, but this is the trend. So this was discussed this week in Brussels, and probably it could be driven by the increase of investment in defense at the European level. So kind of coming back to your point on the dual case. And a last point that I want to also mention is that so regulation, for me, it's part of should be part of a global strategy to drive responsible innovation. But so regulation could be or could occur or not, but it's not the only way to drive responsible innovation. So it may be to prepare the discussion. So.
Yeah, good comment. I agree. I don't know much about law and how we can do responsible innovation. I'm just new. I'm kind of new in this field, but I agree. Regulation is just one tool, I think.
Well, I just want to react to what has been said and ask you a very simple question. From Canada, what's the way you look at regulation? Do you look at quantum computing as something dangerous and regulation based on risk? As traditionally they do at the European Commission, everything is about risk and anticipating possible damages, even if they're dealing with something they don't really understand technically. It's risk before and innovation and science after. And in America, for instance, in the United States, they think exactly the opposite. So what is your own look upon this?
That's a good question. I think Florian would be better suited to answer this than me. But my feeling, because honestly I'm not an expert in this, is that we're a bit in between, but maybe a bit closer to the United States. I think there's no real discussion, real true discussion on how should we regulate quantum now. Maybe there is, but I'm not involved. So I think it's a question of we should position ourselves. We still haven't taken up our position, but I would say that my feeling would be that we're not necessarily completely as the United States, let it be, but a bit more conservative, a bit more like Europe maybe.
Yeah, thank you for your presentation. In artificial intelligence, there is two questions when we go to regulation. It's how we use it and how we create it. Do you think in quantum technology there is the main question is how can we use it for good purposes, or is there also a question on how can we create good quantum sensors or quantum computing, or only on, because for the regulation it's interesting to find what is the right target to regulate. Is it the user or maybe the provider?
Yeah, good question. I think so. On the creation of quantum computers or sensors, I think the main question I've heard or I've thought is on the environmental side. So how much energy will it need to create the computer itself? And I think this is an important question, and it should steer how we create the ultimate quantum computer, let's say, because at the moment there's still so many architectures and we aren't sure which ones will actually work or which ones will be best in a science perspective. But the scientific perspective should not be the only perspective at which we look at this problem. The environmental perspective should also be one, or the energetic perspective. So, but I think that's the only question I see on this side. Thank you.